Good morning. This is Professor Jose Luis Jimenez at the University of Colorado Boulder, and I am recording this webinar to answer the demand for explanation about what does the COVID-19 aerosol transmission estimator do and how to use it. Okay. I'm going to give a brief presentation about what it does, starting from the general and getting more specific. And then I will demonstrate the tool and show some of the key parameters that one needs to set to have a realistic simulation. If you follow me on Twitter, I tend to post any new information there. And the estimator itself is at this link, tinyurl.com/COVID-estimator. So a very brief introduction to the aerosol transmission. I mean, first of all, how did I learn to do this? Well, I have a background in atmospheric aerosols, fluid mechanics, indoor air, and modeling, which are many of the disciplines that come into doing this kind of estimate. I didn't have a background on disease transmission, but I started working on it in March when I joined the group of scientists by invitation from Lydia Moraska that contacted WHO trying to get them to acknowledge the importance of aerosol transmission. And really, we have exchanged literally thousands of emails. And I describe myself, I'm a wingman to the giants in aerosol transmission, such as Lydia Moraska, Don Milton, Lindsay Marr, Julian Tang, people who have been working on this for decades. And anytime I have a stupid question, I ask them an email and they send me 10 papers that address that question in detail. I have done some research now on this topic. In particular, we have investigated the Skagit Choir case, and that's really what convinced me. I was really investigating that case, seeing that there was just no other explanation than aerosols, and just seeing how many transmissions could proceed. That really convinced me that this was an important thing to follow up on. So in the big picture, the aerosol transmission was downplayed by WHO and CDC. WHO, I mean, they're still downplaying it, but other countries like Germany and Japan have accepted it, and they have done better than, for example, the US. Now the evidence, I think, is consolidating that it is major, at least tens of percent, and my opinion is likely dominant, more than 50%, probably 80%. There is not a single argument that I have heard that holds water against it. You can find me in Twitter, and if you look at my pinned tweet, there is a lot of details about why I think that way. You can make up your mind. I still think that fomites, touching objects or touching people's hands and droplets, someone coughs towards you, that can transmit the disease. So I certainly keep washing hands and washing the groceries and all that. I think that's important too. But I think it's also important that we recognize that aerosols are probably driving this disease. So in terms of aerosol transmission of COVID-19, most of the time for most people, it's not very contagious. It's not like measles or chickenpox that are highly transmissible diseases. And it seems that we have to help it along. So at least, with indoor environments, with a long time without masks and things like that to help it transmit. There is also some evidence that at least some super spreading events like the choir, the level of contagiousness starts to approach that of measles. So, my conceptual model of the disease as of right now is, most people are not very contagious through the air, and really only if we help them along in a closed space for a long time and all that, they can transmit. Some people may be very contagious, and then they can transmit more easily, but especially again, they're helped by these situations of indoor environments, etc. The worst situation is face-to-face contact. If you're talking to someone close, because then the aerosols are the most concentrated. Kind of like if someone was breathing out smoke and you are right in front of them talking to them, you're breathing a lot of that smoke with less dilution. So this close contact of close proximity situation is really the worst you can do, or is the best you can do to increase transmission. Then what the estimator deals with is really room level transmission. So you have avoided, you've kept your social distance, you have avoided being within 2 meters of someone, but those aerosols that the person is breathing out are still mixed into the room. And if you are there for long enough, then you may be able to breathe enough to cause infection, as it happened in the case of the choir. That's what we are trying to simulate with the estimator, and that's what what we have some measures that can control, that can reduce that. So far, there is no evidence of long-range transmission. By that I mean, through the ventilation system of a building, the air leaves and then maybe goes through an air handler, comes back, or someone is in a room and 2 hours later someone comes into the same room, or the air moves through a corridor through and many rooms far away. This type of examples are what we call long-range transmission. This does happen for measles, for example. It has not been described for COVID-19, and it seems, I think we can say confidently that this is not driving the pandemic. Whether it happens or not, in some cases, it's unlikely. I think it's difficult to tell, because even for measles, to know that that's happening, you need to have very few cases. There's someone that comes with measles to a town, and then it spreads in a given situation, and then you realize that one of the people who are now sick could only have gotten it through long-range transmission. Right now, with so many cases as we have at COVID, we wouldn't notice, right? And there are papers in the literature about this. But I think the room-level transmission is much more dangerous, and that's what we can fight much better. We do know that outdoors is much safer, especially if you are in an open space, if there is some wind, if during the day, because there is the sun. So then we should move as many activities as we can outdoors. Now, you are outdoors between two tall buildings at night, and there is no wind, and you have a lot of people, that kind of starts to approach an indoor situation. So I would avoid that. But outdoors in an area that doesn't have many walls nearby, there is a little wind, that's much safer. I still wear a surgical mask outdoors, even on those situations, if there is people around. But why not? It helps reduce the probability of transmission. But outdoors is much safer. Okay, so just to illustrate again this close contact or close proximity versus the room level transmission. So smoke is the best analogy we have in terms of helping people think about what are these aerosols. Smoke is aerosols. We see the smoke because those are small particles, they reflect light, and that's why we see them. So in this situation here, if you see my cursor, we have someone who's just exhaling smoke, and you see it's most concentrated right in front of him, right? And it's being diluted with time and with distance. If someone is talking to this person here, is breathing these exhale aerosols with much less dilution than if they are somewhere else in the room and they're breathing this air. So this is, and I believe this is why social distance work. WHO and others say it works because there is these droplets falling that are falling to the ground, and if you're far, they won't fall on you. I think that's wrong. That the reason is that avoiding close contact or keeping your social distance works because you avoid the situations where the aerosols are very concentrated. That can be modeled, and I may add something to the estimator, but we should just avoid it. Room level is harder to avoid. We have to go to the supermarkets, we have to go to the doctor, we may have to go to class. So then that's where we cannot avoid going indoors with people that don't live with us. So that's where the estimator is focused on. What can we do, since we have to do those things, to reduce the chance of transmission, right? And it's more this situation. There is a smoke in the room, and it takes a while to mix and all that, but it's this diffuse smoke that we're trying to fight. Okay? And the estimator assumes that the social distance is kept. Okay? So what does the model do? It's basically a combination of two models. One is what we call a box model in atmospheric chemistry or in indoor air. And literally, you assume you have a box. There is an infective person who's emitting when they breathe, or especially when they talk or sing, they're emitting particles that contain the virus. This is this emission term. And that emission sustains a certain concentration that we call X. That concentration, if the box was totally sealed, it will keep increasing and increasing and increasing. It doesn't for three reasons, because there is three things that reduce the concentration of the virus. One is the virus is some particles that eventually will settle. Gravity acts on them. They may still stay an hour or two in the air, but eventually they will settle. They may also stick to a wall. Also, the virus loses infectivity in the air, and a good estimate is maybe in an hour, it loses 2/3 of its infectivity. And then there is also ventilation. So air comes in that doesn't have the virus from outside, and it takes the air that has the virus outside, and that dilutes it very much. So it's the interplay of these processes. We have a certain emission of a certain strength, and then these three losses, right? And that determines what's the level of virus or smoke that's present in the room, and then how much the susceptible person is going to breathe. The longer the susceptible person spends in the room, the more he or she is going to breathe. If these two people are not wearing masks, then more virus goes into the air and more virus goes into the lungs, okay, or into the respiratory system. So those are the factors that are going to come in the model. Okay. The model mathematically is simple. So there's a single ordinary differential equation that you can solve analytically. Is the same as modeling radon in a house for people who are familiar with it. And the radioactive decay of radon is the same as the virus decay. It's also possible to do a numerical solution, and then you can do any arbitrary situation. And we may do this in a future version, but we haven't done it yet. But for most cases, and for understanding the impact of controls, you don't have to go there. You can just think about, a simple situation. These two people come in at the same time, they stay for a certain period of time, and how much does ventilation help? How much do masks help? That's the best information that you can get from this type of model. And this is why I have preferred to keep the model simple rather than adding lots of bells and whistles that make it then more difficult to understand and more difficult to use. Okay? And I put it on a spreadsheet, again, for a couple of reasons. One is, it's easier to see. I mean, a spreadsheet can be confusing compared to some other interface where you enter numbers and get the result. But a critical difference is with a spreadsheet, all the math is visible. So, helps people understand, and it helps researchers and others take now the model and do creative things with it. There is many things that one can do where you build into this model to investigate other aspects. And I really want to encourage that. You don't need to ask me for permission. If you have some creative idea, just make sure you know what you're doing. But by all means, use the model and do whatever is useful. Okay. So, and as I said, I mentioned the box model. I forgot to mention the Wells-Riley model. So the model that I mentioned, let me go back for a second, will calculate how many infectious doses of the virus, is really the unit we work in, are in the air. But now, then we know how much is the susceptible person breathing. What's the probability this person gets sick? That's where we use something called the Wells-Riley model, developed by those two researchers in the 20th century to investigate tuberculosis in particular, and very successful at predicting that. And there is one thing, this is a detail, but some people worry, well, how many viruses are exhaling? How many of those are viable? Where do they deposit? What's the chance that a deposited virus may lead to infection, depending if it deposits in the nose or in the lung? Those are very complex processes that are very uncertain. And the genius of the Wells-Riley model is that they lump them all together into a quantity called an infectious dose or a quanta. And then you don't have to represent all those processes explicitly, and you can fit outbreaks and then get a real idea of these infectious doses by fitting outbreaks of a given disease, and it's going to be different for different diseases. Okay? And there are links on the spreadsheet where you can read more about this if you care. But it works, which is what matters. Okay? So in terms of what's useful for the model, I think you can get an order of magnitude estimate of the risk. So if you run a certain classroom, a certain situation, and you say there's a 2% chance that you will get infected under those circumstances, well, that 2% you have to take with a big grain of salt. Maybe it's 0.5%, maybe it's 10%. Right? So it's giving you maybe within a factor of 5 or a factor of 10, really, of the risk. But it's not 0.001%, and it's not 100%, right? So that's kind of how to interpret the probability of the model. It would be better to have something more accurate, but we just don't know enough about this disease. Okay? And it's also known, I think, that people are variable, as I was mentioning earlier. Some people maybe emit more infective particles. So you also don't know in the particular supermarket or classroom where you're going to be, are you going to have an infected person that emits a lot of particles or fewer particles, right? So that's why we have to take the absolute number as with a grain of salt. It could be higher and it could be lower. Okay? But the most important use of the model is to understand the mitigation measures. So the model makes it clear that we should meet outdoors when it's feasible. It makes clear that we should increase ventilation by opening the windows, by having more outdoor air in mechanical ventilation, by adding better filters. It also makes clear that you can use things like portable HEPA filter units and maybe germicidal UV, and those techniques also reduce the infective virus in the air and reduce the chance of transmission. There is many people selling lots of things and selling lots of them with the name of air cleaners, with ions, plasmas, oxidation, and people who want to spray bleach into the air or different disinfectants. My recommendation is to stay away from all that. Some of it, is not well understood. Some of it may work a little bit, but actually some of it may be dangerous, and it's just not well regulated. So I would say go with HEPA filters or with ventilation, and if you really, really need it, go with germicidal UV. But if you have a HEPA filter unit, it doesn't need to have UV inside of it because the virus is already trapped. So germicidal UV would be to put in air ducts or to put in a ceiling, and you never want people to be exposed to the UV. That would be dangerous. Okay? So you have to know what you're doing, which is one reason why we don't recommend it very widely. Okay? Something else that you learn from the model is you understand the physical processes. You understand what's going on. So you can think of things to do for your situation that I haven't thought about. I get emails from people in India and they, I explain what's going on and then they say, oh, in where we live, the houses are very close and then opening the windows actually is worse. And people have all kinds of creative ideas about how to deal with the risk in their situation that you see. We just gave guidelines, a little bit like WHO says, it's like, oh, you have to ventilate, but they don't say why. So then people cannot think for themselves. I think that's actually the most powerful reason to do a model like this. And as I said, you can incorporate this into more complex models that do other things. And it makes clear what the parameters are needed when you want to investigate an outbreak. What do you need to record? One really frustrating thing for a lot of outbreaks is, they report, oh, there was this outbreak and this many people got sick, but they don't record the size of the room or the ventilation characteristics. And without those, it's very difficult to obtain a quantitative understanding of transmission by the air. So if you are someone who is investigating outbreaks or documenting outbreaks, please record all the parameters in the model, but especially the ventilation rate and the dimensions of the space. And if you have questions, you send me an email and I can help you with that. Okay. One important detail, which I have made clear in the latest version, you have two ways in which you can think about the model. One is, I do the calculation assuming there is one infected person present. So for example, there is a class with 30 people and I assume one of them is infected. What's my chance of getting infected? That's what we call the conditional probability. Is the probability conditional to the assumption that there is one infected person? But for example, in my city right now in Boulder, out of 30 people, there's not one that's infected. It's maybe one out of every 1,000 or every 3,000. Right, so the absolute probability says, okay, I have a probability, let's say 3% of being infected if there is someone infected in the room, but now there is a 1% probability there is someone infected in the room. So the total probability is the product, 3% times 1%, right, which is a much smaller number. And that's what I call the absolute probability, and that's the most realistic result. If you are analyzing an outbreak where there was someone infected that gave the disease to the people, you need to use the conditional probability. Or if you want to analyze a worst case scenario, you say, if I'm going to go to the supermarket or a class and I don't know if 6 people are going to be present or not, it's possible, then the absolute probability is what you need. Okay? And again, to repeat, this is only for the room level aerosols by breathing or talking. We're assuming that we're avoiding close proximity, we're avoiding touching objects, or we're washing our hands, so we're not having this fomite transmission, and that people are not coughing or sneezing. If any of those things are not true, there is additional risk of transmission that this estimator doesn't account for. Now, a couple of things about masks that is a little tangential, but I think it's so important that I should take advantage of the opportunity to say them. The first one is fit is critical, and it may be more important than the quality of the mask. And I'll show a video in a moment. The video is linked here. And this is a surgical mask, and you can see how as the mannequin breathes out, this smoke containing particles, we see that because there are gaps and here and there, we see all this smoke that comes out. It comes out towards the back. So if you are near a person who's not wearing a mask very well, where it's not very tight, you don't want to be behind. Actually, in front is the safer location. Now you see here for this KN95 mask, this nominally is better, but still they didn't fit this wire around the nose very well, and you see it still has leaks. Again, they go towards the back. And here there is in the video, they also show a cloth mask, and this mask is very well fit, and you cannot see any smoke coming out. Okay, so even though we would think, okay, this is the better mask than this one and that one, in reality, the order is scrambled because fit matters a lot. Okay, and actually, I won't show the video in the interest of time. You can see it here, but basically, it shows what I just showed, and this was done by Philomena Blissen, who's one of the members of our group of scientists who've been communicating with WHO. The other thing that's very important about mask, when we talk, we emit 50 to 30 times more particles than when we're just breathing. So you have a group of people and one of them is gonna talk, don't do what we see on TV, that the person who's gonna talk removes the mask. Even Tony Fauci has made this mistake. The person who's talking is the person that's most important that they're wearing the mask, okay? So it will be, the analogy I'm using is like removing your mask to talk is like lighting your cigarette when you're entering the elevator with other people. That's the worst thing you can do. So yeah, you can understand people less well and all that, but transmitting the disease is much worse. Now an example of the things you can do with the tool before we go into more details. So for example, this is the Skagit choir, that we have fit, and in the real event, you have an 80-some% chance of transmission, right? But now we can say, what if? Once we have a model that works, there is nothing more practical than a good theory. Once you have a good theory, a good model that works, then you can say, what if we had done this? What if they had done that? So every case here, we're doing one thing at a time, except in this one in which we do multiple things. So here we're saying, okay, it's the choir, but we increase the ventilation to 3 per hour, which is significantly more than they had. The chance of transmission goes down quite a bit. Now we go back to the real case, but we add a portable HEPA filter. Again, the chance of transmission goes down quite a bit. Now we go back to the original case, but they were all wearing well-fitted surgical masks. Again, the chance of transmission goes down quite a bit. Now we shorten the duration. Instead of 2.5 hours, it was 1 hour and a quarter. Again, the chance of transmission goes down quite a bit. This was a case in which the emission of virus into the air was very high. So any one of these measures cannot control the transmission completely. But now let's say that we do all these 4 things together. We increase the ventilation, add a portable HEPA filter, we add well-fitted surgical mask, and we shorten the duration. And now we have gone from 80-some% to maybe 8%, okay? So a factor of 10, right? And this is what we can learn from this tool. It's like all the things that we can do, none of them is the magic bullet, right? But they all help, and we need these layers of controls to help us defeat the problem. Okay? Now let's say we can do another case scenario. Let's say we do the real event, but this was a situation in which instead of people singing, they were just talking, because singing really enhances the emission of respiratory particles. So this again lowers the chance of transmission a lot. And now if we did exactly the same thing, the same choir, but we did it outdoors, actually the probability of transmission, it depends exactly how outdoors, but the probability of transmission is minuscule. Okay? So this is when musicians are contacting us and say, what about my choir, or if I have wind instruments? Well, unfortunately, as the doctors call them, singing in a choir or playing the trumpet or the oboe or the saxophone is an aerosol generating procedure. It's like, unfortunately, it really enhances this production of particles that may have the virus if a person has the virus and doesn't know it. So really outdoors is and masks and with distance and in the sun is really what we recommend to continue those activities. Now we're going to using the estimator. Okay? So again, repeating, the infection probabilities themselves are very uncertain and they're likely variable with the person. And the most important thing is the relative impact of controls. Okay? As of today, the 22nd of July, you should use the master sheet, which I have basically, the calculation is the same, but I have just tried to make it a lot clearer based on the feedback I get, what people find confusing. You should read the README page and the frequently asked questions sheets. I understand they're long, but at least look through the headings about what's being discussed. I get many questions that are already answered there. And when people do, I mean, many people use the estimator and get the wrong answer. And in general, it's because they haven't taken the time to think about the details and to read about it. Okay? And in your case, you need to, there are some inputs that are really essential to change for your case, right? The most important is what's the probability of having someone infected? And I will show a web page. This can be estimated from the prevalence of the disease. For the US, there is this website, which is linked on the README page. And for example, you can say, okay, I'm gonna look in Colorado, I'm gonna choose the county of Boulder, where I live, and I have 10 people in the room, which is what's allowed right now. I see the calculation and it tells me, okay, there is a 0.8% chance that someone in the room has COVID-19. Okay. In this model, they assume that for every diagnosed case, there is 5 undiagnosed cases. That seems a little high to me, so I would maybe take this number and divide it by 2. But anyway, that's something you can do. For this only works for the US. For other places, you can go to like the New York Times database or the Johns Hopkins database and basically do the same calculations that are described here. And that's very important because in an area with low prevalence of the disease, just the chance of contagion is lower. Now the quantum emission rate, this is the most uncertain parameter for a new disease. Okay? We know it's going to be proportional to the emission rate of respiratory particles, and there is data on that, and we calibrate it to the outbreaks, but at least I would say any number you pick is maybe uncertain by a factor of 5. It could be a factor of 5 larger or a factor of 5 lower or even more than that. The ventilation rate is very important. And in many spaces, you don't know what the ventilation rate is. There are ways if you have a CO2 sensor, or if you look at the literature for typical houses, maybe 1 per hour. If you open the windows, it will be larger, much larger if there is wind, less so in a still day. You can also experiment with the smoke, light a match and see, how long does the visible smoke take to dissipate, right? So anyway, that's a very important parameter. And if you work in a commercial building or in a university, basically the building proctors, the people in charge of the building should know that number and should be able to provide it. And also the breathing rate is important, which depends on activity. If someone is resting, they're breathing less air and they are producing less particles. And if someone is exercising, if they're singing loudly, then they're breathing more air and that increases the chance of transmission. So all of those parameters you have to change for your particular case. So now let's have a look at the estimator itself. So it's here in this Google spreadsheet, which is with the link I gave before. I cannot let people edit this one because we can see right now there is 96 people using it and they will all be overwriting each other. And unfortunately, there's no way about that. You have to make a copy. So you can, if you click on this link, it will make a copy on Google Sheets if you prefer that format. If you click on this link, it will download into Excel and you can then use it in whichever of those ways. The only annoyance with this situation is then I keep making changes, I keep making it better or clear, whatever, but you're stuck with an old version. So I would say, you can look at the bottom of the spreadsheet. I see which updates I'm making, but if some time goes by, you may want to consider making another copy or downloading another version. Okay? And I want to thank many people who have provided input and have found errors and have provided more information. This is really a group effort. I also maintain an email list that I'm going to use to basically distribute information about this so that I can know who's using it and I can provide information, especially if we find an error, if we develop some useful new feature. And as I said, my Twitter feed is also where I put information on this. Okay, so this is the README sheet. And here it explains what I said. This is where we're trying to estimate. This is these are the assumptions, and this is how to use it. And these are the papers where the science is described. And here we get into a description of all the parameters. Okay? So here we have the quanta of emission. So for example, there's a number you're gonna have to enter in the spreadsheet. So you have to decide which of these situations is closest to what you're simulating. If you say, okay, I'm standing and speaking, so then maybe you will use 11. And I'm standing and loudly speaking, I will use 65. And then you say, well, it's loud, but not very loud. Well, then use 30. I mean, this is, at the end, it's uncertain, so use your best estimate. Okay. Then you have the inhalation rates. How much air do we breathe? Which again is an important. So this is going to depend on the age, and you would use the mean. These are in cubic meters per day. In the spreadsheet, we use them in cubic meters per hour. So make sure to divide this by 24. Okay. Then the efficiencies of the mask in reducing the virus coming out from the infected person. So here we have some values. I've been using 50% for a typical mask in the community. You know, there are other values here. You know, if you know better, if the masks are very good or are very well worn, then if you can use a better number and so on. Now there is also the efficiency of the mask in reducing the inhalation of the virus. And I've been using, again, 30% for a typical mask. Perhaps it's a little higher, but you know, in the community, many masks are not well worn. Some people wear them below the nose. Some people have a lot of gaps. They don't wear it tightly. So you know that this accounts for all of that. If you know, if you're in a situation in which everyone is being really conscientious, you may be able to use a higher number, like 50%. The building ventilation rates. Okay, so this is, so for a house, I would use 1 per hour. If it's a modern, very airtight house, maybe half per hour. If it's a house that's leaky, maybe 1.5 per hour. You know, if you have the windows open, if there is no wind, maybe 3. If there is a lot of wind, maybe 15. You know, something in between. And these are values from classrooms. It depends. You know, older buildings, they can be leakier, but also they tend to have worse mechanical ventilation. So maybe values of 1 or 2 are typical. In a good university classroom, it may get as high as 10. In a hospital, it's 6 to 12, right, depending. And here for the US, and I think it's similar in Europe, you can enter certain parameters from this table from the ASHRAE, the American Society of Heating, Ventilation, Refrigeration, and Air Conditioning Engineers. And you can say, okay, I am in an art classroom, and you can read the numbers here, enter them in this little worksheet, and it will give you an estimate. This is for modern buildings. Okay, older buildings follow older standards, and this may be lower, but at least this gives you an idea of the upper limit. Now, the decay rate of the virus indoors. Okay, there are multiple studies, and I listed here the 4 I'm aware of. They don't all agree, right? I mean, they give numbers that range between 0, the virus doesn't decay, but that's really the weakest of the studies, to something like it decays once per hour or something like that. And there is also some dependence on temperature and humidity. We know that the temperature really degrades the virus, and we know that low humidity helps preserve the virus. And in fact, this is thought to be the reason why we have a flu season, because indoors we have lower humidity in the winter. Also, people spend more time indoors, and that's why we have more cases of the flu in winter, and that's why we fear we may have a lot of cases of COVID this winter. That can be taken into account with this calculator. I have written to several of these researchers to see if I can get some consensus, but right now, I believe I'm maybe using the value from Van der Malen, which is this one. But anyway, again, you could try different numbers and see. The deposition of the virus onto surfaces, it depends on the size of the particles that the virus is carried by. Bigger particles settle faster, maybe in half an hour. Smaller particles may take 4 hours, right? I'm taking the 4-hour limit. This is something that's also uncertain. Now, if you have a portable HEPA filter unit, this is how you do the calculation to get the number that you enter in your spreadsheet. What's the probability that someone is infected? Again, I explained it here, but for the US, I would go to this site that I already demonstrated. And I would probably take the number there and divide by 2, unless you are in an area that really you have an outbreak out of control and the test can't keep up, like maybe Arizona or Texas right now. Then maybe I would take the number from the webpage at face value and use that one. CO2, this is a side point. You can completely ignore it, but it is of interest because CO2 is in an indoor space is an indicator of how much exhaled breath is there in that air, which is proportional to the risk of infection. Okay? So there are these tables, and you can calculate CO2 with a model. It's very similar. It has some limitations, which I described on the FAQs, but this opens the way to using a CO2 sensor in a space and using that as a risk indicator. If the CO2 goes up, oops, we need to stop. Or maybe the ventilation system has failed. If the CO2 level is lower, then we are safer. So it's like some indicator of safety, even though it is imperfect. And here at the end, I have the version logs and the things that I plan to improve if I have time. Okay. Next, we have the frequently asked questions. And here, you can read them, but it's basically, I try to explain the answers to the questions I get all the time. Okay? And I don't have time to go through this, but I explain more about, what is a quanta, what should we use, and many different things. Okay? So now let's go to the spreadsheet. This is the master spreadsheet as of today. And again, what I'm gonna try to do is all these other ones, the classroom and the choir and whatever, I'm gonna update them using the spreadsheet because I think it's clearer, but I just need to improve a couple of things. Okay? So this is color coded. Okay, each section is in green. The important inputs that you really need to specify for your case are in orange. Okay, and the other more specialized inputs that they are variable or uncertain, but most people will want to leave them alone, are these one in yellow, and the results are going to be in blue. Okay, so what do we need to know if we want to predict the chance of transmission in a classroom, or if we are analyzing an outbreak? We need to know the volume of the room. Okay, so you have this little calculator here, and at the end you need the volume in cubic meters. We also need to know the duration of the event, how many repetitions of the event. So for example, if it's a class in a university and we are doing it 30 times during a semester, this would be 30. In this case, I'm actually simulating the choir case, so it will be a one time. Then the ventilation rate in units of per hour. Okay, so this is gonna matter a lot, and these are the units that ventilation experts like, liters per second per person, and they are related, but here we have to enter them in per hour. Okay. Now, how many infective people there are? So normally we're going to say there is one, and I'll explain the conditional versus absolute probability later. And how many susceptible people there are, which here for the choir, I'm assuming there were 60. If you are now in New York, where maybe 20% of the population has had the infection and maybe immune, if there are 60 people, you would enter here 48 people, because only 48 people are susceptible. The other 12 are immune. Okay? And maybe I'll add that to the spreadsheet as well. Now the breathing rate. Okay, so in this case they were singing, so this is 1.5 cubic meters per hour. Again, remember that the cubic meters per hour, that the tables from EPA show in cubic meters per day. So we have to take, if you take a number from there, you have to divide by 24. Or if they have it in cubic meters per minute, which I think is what I did here, then you have to multiply by 60. Okay, be careful with the units, otherwise the results will make no sense. Okay. If you care about the CO2 calculation, this number is also very important from the tables in the README page. Okay. And this is the most important number, which is this quanta exhalation rate, and it's very uncertain. Okay. And here you enter the efficiencies for the masks. Okay. If they were wearing masks, this would be 50%, 100%, and 30%. But for the choir, we leave them at 0 because they were not wearing masks, they didn't know at the time. And the probability of being infective, and this is again calculated for that case, they had a probability of 1 in 10,000 that one person was infective. They were unlucky, they were unlucky in that particular choir. They won the lottery, or they lost the lottery, and they got a person who was infected and didn't know it, and that caused the outbreak. Okay. Then we have these numbers of the hospitalizations rate and the death rate. Here I have 4% because the people in the choir were older, Otherwise, I would have used 1%, right? So you enter all those numbers for your particular case, and then here you get the results. So here you get the conditional results for one event. We do this thing once, okay? And we run the model through these equations, and then we get a conditional result. If there is one person infected, right, the probability of infection was, 80-some%, right? And the probability of death was this much. And this is the probability for one person. One person attending had an 88% probability of being infected. Now this is different, and for yourself you care about this result. But if you are the organizer or you are running a university or a school, you care about the probability or the outcome for all the attendees. Okay? And in that case, this is the output you want: how many cases appear and how many hospitalizations and how many deaths. Okay? And these are the results for CO2. And you see in this case, the CO2 level would have been about 2,500 ppm, right? And this indicates that air was dangerous. My colleagues are suggesting 600 to 800 of being safer, and definitely had the ventilation been able to keep the CO2 at 600 to 800, they would have had many fewer infections. Okay? And now we have the absolute result. Let's assume that now we're studying, a different choir, maybe in the same region, but they may or may not have someone who's infected, right? And then, so it's basically the same calculation, but now the chance that you have someone infected in that room is 0.007 or 0.7%. You redo the calculation, and now the probability of infection for one person is 0.59%. And for all the attendees of the event, the number of cases that appear is 0.36%, 0.36 cases. Sorry. Now this is what matters in terms of do a calculation for a class that may be held, or for a choir rehearsal, or whatever other thing that you may do. These are the numbers that matter to you. Okay. And now this is one more calculation. Is the same absolute result, but if you do the event many times. I pointed out that number above. We said one time, but this is now if you do it 5 times or 20 times. Here, because we're doing it once, the numbers are the same. If I increase the number of times, then this is going to increase. Okay. So this is a description of the spreadsheet. You need to spend time understanding what things are, especially if you're not familiar with models or spreadsheets. But now let's do some control, right? We were saying we had 83% chance of infection for an individual. Let's do something. Let's say, well, we're going to increase the ventilation, and we're going to say, okay, it's going to be 3 per hour, and we're going to get some HEPA filters that are going to give us an additional cleaning of 2 per hour. And we're going to shorten the duration, so we're going to do 90 minutes instead of 150. And we're going to use masks. So we're going to use masks, so they're going to limit exhalation by 50%, and 100% of the people are going to wear the masks, and 30% inhalation efficiency, right? And in the same probability of infection. So this is basically the kind of thing we can do, right? And now we look at the probability of infection, and it has gone down from 87% to 13%, right? This is a case, as I said, where the emission rate of the infectious particles was very high. For a more typical situation, let's imagine this is a classroom and someone is talking, maybe a more typical number would be 100 infectious doses. And now the probability of infection is 1.5%. Okay. So then, something that shocks some people who have believed that, okay, if I keep my social distance, my chance of infection is 0. That's not correct. If you go indoors with other people that don't live with you, you have some chance of infection. It's not 0. The best is to not go, to do things remotely, or to go as little as possible, to buy your groceries online and pick them up at the door of the store, whatever thing like that. But we can do many things, we can do many things to reduce the probability of infection. Okay? So anyway, and one thing I mentioned, so let's go back to the choir case, and we have this, and now let's say everyone was wearing masks, but the one person that was infected was not wearing masks. Now we go from 13% to 25%. So really, the person speaking really needs to wear masks in all cases. Okay, so this is all I had to say. I hope it was useful and not too long. what I'm gonna do is I'm gonna do now a webinar in real time for question and answer. Okay? I think everyone can listen to this recording, and then maybe in a day or two I will organize it and announce it, and then we can do a webinar when people can ask questions and we can discuss. And people have very good questions, and every time people ask questions, I end up improving the estimator. So thanks again for your time. Thank you very much.